Tonight, we drift alongside one of the strangest worlds in our solar system, a moon smaller than Earth's own, scarred, frozen, orbiting a giant that may be hiding more liquid water than exists on the entire surface of our planet. A world scientists have been watching for 4 centuries and studying seriously for 3 decades, and still cannot fully explain. Over the next few hours, we'll descend through what we know about Europa. Through the ice, through the evidence, through the instruments that have spent years listening for signs of what lies below. Through the mission NASA has already launched to go closer than anyone has gone before. There is no urgency here, no rush. Only the slow accumulation of something remarkable, carried quietly through the night. We have time. In December of 1995, a spacecraft called Galileo arrived at Jupiter after 6 years in transit. It had launched from the cargo bay of the space shuttle Atlantis back in October of '89, a slow, looping journey that took it past Venus once and Earth twice, before gravity finally bent its path outward toward the outer solar system. By the time it reached Jupiter, the team at NASA's Jet Propulsion Laboratory in Pasadena had been waiting nearly a decade for what came next. Galileo wasn't sent specifically to look at Europa. Jupiter was the target, its storms, its magnetosphere, its 4 large moons as secondary science. But on the 4th of January 1996, the spacecraft made its first close pass of Europa. And when the magnetometer data came back, the instrument measuring the local magnetic field, something in the numbers didn't fit. The signal was off. Subtly, specifically, persistently off. A researcher named Margaret Kivelson at the University of California, Los Angeles, was part of the team responsible for that instrument. She looked at the anomaly and began asking a question that would take her 2 more years to answer properly. Something beneath Europa's surface was conducting electricity. On the 7th of January 1610, a man in Padua pointed a tube at Jupiter and wrote down what he saw. Galileo Galilei had been grinding his own lenses for months, improving on a design that had come out of the Netherlands the year before. His instrument was not the first telescope, but what he did with it on that January night and on the nights immediately following changed the architecture of everything humanity thought it knew about its place in the universe. He saw 3 small points of light near Jupiter, faint, aligned, close. He assumed they were background stars and noted their positions. The following night, he looked again. The points had moved. Not the way background stars move, slowly, predictably, with the rotation of the sky. These had shifted relative to Jupiter itself. By the 10th of January, a 4th point appeared. By mid-January, he understood what he was seeing. 4 small bodies orbiting another world. Not orbiting Earth, not orbiting the Sun, orbiting Jupiter. He named them the Medicean stars, after his patrons. Later, they would be renamed the Galilean moons. The 4 largest moons of Jupiter, Io, Europa, Ganymede, and Callisto, carry his discovery in their collective name to this day. Europa was the second one from Jupiter, the smallest of the 4. In Galileo's telescope, it was nothing more than a point of light, indistinguishable from the others, moving in a quiet orbit around its giant host. He had no way of knowing what it was. He was simply the first human being to know it existed. It would be 369 years before anyone looked at Europa and suspected there might be an ocean there. The spacecraft named after Galileo was conceived in the 1970s, approved in the early 80s, and had a journey to launch that was almost as complicated as its journey to Jupiter. It was originally intended to fly in 1982, then 1984. Then the Challenger disaster in January 1986 grounded the entire shuttle fleet and delayed it further still. There were engineering problems, budget disputes, a complete redesign of the trajectory after safety concerns ruled out the direct route. By the time Galileo finally lifted off from Kennedy Space Center in October of 1989, the scientists who had first proposed it were considerably older than when they'd started. Torrance Johnson was the project scientist, a planetary scientist at JPL who had worked on the mission concept since the mid-70s. He would later describe the launch as the moment a 15-year argument finally left the ground. The spacecraft carried 12 science instruments. Among them was a magnetometer built by Margaret Kivelson's team at UCLA, designed to measure the magnetic environment around Jupiter and its moons. Nobody at that point expected it to find an ocean. It was there to study Jupiter's magnetosphere, which is the largest planetary magnetic structure in the solar system. Europa was a scheduled stop, an interesting secondary target. The ocean found the magnetometer before the magnetometer found the ocean. That is roughly how discovery works. You point your instruments at one problem, and something else entirely reaches out and touches them. You spend the next 2 years figuring out what just happened. By the time Kivelson's team published their analysis in 1998 in the journal Nature under the title, "A Magnetic Signature for a Subsurface Ocean in Europa," the small point of light that Galileo Galilei had noted in his journal on a winter night in 1610 had become the most compelling candidate for extraterrestrial life in the solar system. 4 centuries, one question gradually sharpening. Europa is not supposed to have liquid water. On paper, it has no business being anything other than a frozen rock. It sits roughly 485 million miles from the sun, so far that sunlight arrives there at about 4% of the intensity we receive on Earth. At that distance, with no thick atmosphere to trap heat, the surface temperature on Europa hovers around -160 degrees Celsius. Cold enough that the ice is harder than granite. Cold enough that any water exposed to the surface would freeze solid and stay that way, essentially forever. And yet, the ocean is there. And the reason it's there has nothing to do with the sun. It has to do with Jupiter. Picture squeezing a rubber ball in your hand. Not hard, just gently, rhythmically, over and over. The ball warms slightly in your palm, not from the temperature of your hand, but from the energy of the squeezing itself. The repeated deformation of the material generates heat from the inside. This is roughly, very roughly, what Jupiter does to Europa. Europa orbits Jupiter once every 3.5 days. It doesn't orbit in a perfect circle. Its path is slightly elliptical, which means sometimes it's a little closer to Jupiter, sometimes a little farther. That varying distance means Jupiter's gravitational pull on Europa changes constantly. Stronger, then weaker, then stronger again with every orbit. And that changing pull flexes Europa's rocky interior. Not dramatically, not visibly, but persistently, continuously, over billions of years. The technical term for this is tidal heating. The same basic mechanism that causes tides on Earth, the moon's gravity pulling the oceans, but applied to a solid rocky body and amplified enormously by the fact that Jupiter outweighs our moon by roughly 25,000 times. That constant flexing generates heat, and that heat, accumulating in Europa's rocky interior over 4.5 billion years, is enough to melt ice from below. Think of Europa this way. Imagine a hard-boiled egg. The shell is the ice layer, hard, cold, cracked with age. Beneath it, the white, liquid water, a global ocean wrapping entirely around the world. And at the center, the yolk, the rocky core, warm, flexing, the source of everything. The ocean doesn't sit in a basin the way Earth's oceans do. It wraps the entire interior of the moon, sealed above by ice and resting below on rock. That image, shell, ocean, core, is the model scientists work from. What they disagree about is how thick the shell is. Current estimates range considerably. Some models suggest the ice is no more than a few kilometers deep in places, geologically thin, perhaps cracked all the way through at points by the same tidal forces heating the interior. Other models argue the ice is 20 to 30 kilometers thick throughout, a massive rigid lid that has sealed the ocean from space for billions of years. The difference is not academic. A thin ice shell means material can cycle between the ocean and the surface relatively easily. Chemicals from the ocean reaching the surface, oxidants from the surface being pulled down into the water. A thick shell means the ocean is far more isolated, a closed system that has been running entirely on its own chemistry since before complex life existed on Earth. Europa Clipper carries an ice-penetrating radar instrument that will attempt to measure the shell thickness directly during its flybys. This is one of the central questions the mission was designed to answer.
But here is what both models agree on. The ocean is real, it is global, it is liquid, and it has almost certainly been liquid for a very long time. Not intermittently, not seasonally, continuously. A standing body of water that has been there, sealed beneath the ice, since approximately the formation of the solar system. 4.5 billion years of ocean, in the dark, waiting. Consider every drop of water on Earth, every ocean, every sea, every lake and river and glacier, every cloud carrying rain toward a coastline, every aquifer sitting silent beneath a dry plain, every ice sheet pressing down on Greenland and Antarctica. All of it, every body of water this planet has produced in 4.5 billion years of geology and weather and life. Now multiply it. Europa's ocean is estimated to hold roughly 2 to 3 times that total volume. A world considerably smaller than our own moon. A moon of a moon, essentially, containing more liquid water than exists anywhere on the surface of Earth. Not a comparable amount, not a similar amount, more, significantly more. Stored beneath ice, in the dark, on a frozen body orbiting a gas giant that most people couldn't point to in the sky without help. There is something quietly disorienting about that number. Not because it's large. We've barely started with large numbers tonight. But because of what it does to the assumption that Earth is where the water is. That assumption, it turns out, was only true because we hadn't looked far enough. The surface is still. It has been still for a long time, longer than any stillness you have ever sat inside, longer than the oldest quiet place on Earth. The ice stretches outward in every direction, pale and smooth in some places, buckled and ridged in others, where two great plates met long ago and pressed against each other with the slow patience of things that have all the time there is. The frost lies soft in the low places, in the shadows along the ridge lines, where Jupiter's light does not quite reach. It settles in thin drifts, fine as powder, cool and undisturbed. Nothing moves it. There is no wind to carry it, no season to shift it, no morning to change the angle of the light. It simply rests, the way very old things rest, without effort, without awareness, without any need for anything to be different than it is. Jupiter fills the sky above, vast and slow and amber, its bands of cloud moving in long arcs too gradual to follow with the eye. The light it casts is soft, not the sharp white light of the sun, but something gentler, warmer, a reflected glow that falls across the ice and finds no shadow deep enough to fully darken. The surface receives that light the way a sleeping face receives the glow from a distant window, passively, without response. The horizon is low and curved. Europa is small enough that the horizon bends noticeably, the ice falling away on all sides into a gentle curve that makes the world feel both intimate and boundless at once. Standing here, if standing were possible, if warmth were possible, if any of the conditions for a human body existed in this place, you would feel the smallness of the world beneath you and the enormity of the sky above you simultaneously, and the two sensations would not contradict each other. A faint aurora threads along the horizon to the south, where Jupiter's magnetic field reaches down and touches Europa's thin atmosphere. A shimmer of pale blue and green, barely there, moving in slow pulses like something breathing. It has been doing this for as long as the ice has been here. It will be doing it long after tonight. The cold settles into everything, into the ridges and the frost-filled valleys, into the ancient brown streaks that cross the plains like the memory of something that once moved through here and left its mark. Into the silence, which is complete and deep and soft-edged, the kind of silence that doesn't feel like absence so much as presence. The presence of a place that has been exactly itself for an almost incomprehensible span of time, and is in no hurry to be anything else. Below the surface, far below, something stirs. But up here, there is only the ice and the light and the stillness that holds it all. For most of the 20th century, Europa was a surface. That was all anyone could study: the exterior, the ice, the colors and cracks visible through telescopes of increasing quality. Scientists could measure how Europa reflected light, could estimate its surface composition, could model its orbital mechanics and calculate the tidal forces acting on its interior. They could build theories about what might lie below. But a theory about the inside of a moon, constructed entirely from observations of its outside, is a theory with nowhere to stand. The model suggested something interesting might be happening beneath the ice as early as the 1970s. In 1979, a paper by Stanton Peele at the University of California, Santa Barbara, along with Patrick Cassin and Ray Reynolds at NASA Ames, calculated that tidal heating from Jupiter should be generating significant heat inside Europa, enough potentially to maintain liquid water. The paper was published just days before Voyager 1 flew past Jupiter and sent back the first close images of Europa's strangely smooth, cracked surface. The timing felt almost staged. Here was the theory, and here, immediately after, was a surface that looked exactly like what a theory about liquid water beneath ice would predict. But looking like something and being something are different problems entirely. The cracks could have other explanations. The smooth plains could be explained by surface processes unrelated to a liquid interior. The theoretical heating calculations were models built on assumptions. Convincing evidence, the kind that moves the scientific community from intrigued to committed, required something the telescope couldn't provide. It required going there. The Galileo spacecraft carried a magnetometer
for reasons that had nothing to do with subsurface oceans. The instrument was designed to study Jupiter's magnetosphere, the enormous bubble of magnetic influence that Jupiter projects into space, larger than the Sun itself. Europa was one of several moons scheduled for flybys, each one an opportunity to take measurements in a different part of that magnetospheric environment. What Margaret Kivelson's team found during the first Europa flyby in January of 1996 was a disturbance in the local magnetic field that didn't fit the Jovian magnetosphere models. The field around Europa was behaving as though something inside the moon was responding to Jupiter's rotating magnetic field, generating its own induced magnetic signature in reply. There is only one class of material that behaves this way in response to an external magnetic field: electrically conductive material. And the most plausible electrically conductive layer inside a small icy moon at the depths and temperatures the data implied was a global saltwater ocean. Kivelson spent 2 years building the case, cross-checking flybys, ruling out alternative explanations, tightening the analysis. In 1998, the paper landed in Nature. The ocean hadn't been seen, it hadn't been touched. It had announced itself through physics, through the way it disturbed a magnetic field passing through a moon 400 million miles from Earth. That announcement is what we're still following. Here's the problem Margaret Kivelson was looking at in January of 1996. Jupiter has a magnetic field. Every planet with a molten, rotating metallic core generates one, Earth included. Jupiter's is the most powerful in the solar system, roughly 20,000 times stronger than Earth's, projecting a bubble of magnetic influence called a magnetosphere that extends millions of kilometers in every direction. As Jupiter rotates, once every 9 hours and 55 minutes, faster than any other planet, that field rotates with it, sweeping through the space around Jupiter like the beam of an enormous invisible lighthouse. Every moon inside that magnetosphere sits inside that rotating field. It washes over them continuously, changing direction and intensity as Jupiter turns. Now, if you take a conductor, any electrically conductive material, and move a magnetic field through it, the conductor responds. It generates its own magnetic field in reply. This is called electromagnetic induction, and it is the same principle behind every electric generator ever built. Coil of wire, moving magnet, current flows. The physics is unambiguous, and it has been confirmed in laboratories for nearly 2 centuries, since the work of Michael Faraday in the 1830s. What Kivelson's magnetometer detected near Europa was a magnetic field that didn't belong to Jupiter. It was smaller than Jupiter's field. It was oriented differently. And, this is the part that took months to fully work out, it was changing direction, not randomly. Not in a way that suggested Europa had its own permanent internal magnet. It was changing direction in sync with Jupiter's rotation, as though something inside Europa was responding to the sweep of Jupiter's field every time it passed. Something conducting electricity. Something generating an induced field in reply, the way any good conductor would. The question was, what?
Europa has a rocky core. That much the orbital mechanics confirmed. The moon's density and gravitational behavior are consistent with a silicate interior. But a rocky core at Europa's interior temperatures, without the violent volcanism that drives Io's extraordinary activity next door, is too cold to generate a strong global magnetic field through dynamo action. Earth's magnetic field comes from a liquid iron outer core in constant churning motion, a process that requires temperatures above 3000 degrees Celsius deep in the interior. Europa's rocky interior simply doesn't reach those conditions. So the field Kivelson's instrument was detecting couldn't be coming from the rock. The only remaining candidate was a conducting layer between the rocky core and the frozen surface. A layer at the right depth, the right temperature range, with the right electrical properties to produce the observed signal. Salt water conducts electricity. Seawater on Earth, with its dissolved sodium and chloride and magnesium and sulfate, is a reasonably good conductor. Not as good as metal, but good enough. Good enough if the layer were global and deep to generate exactly the kind of induced magnetic signature Galileo was detecting. This was not a small inferential leap. It was a specific, testable, physically grounded prediction. If Europa had a global saltwater ocean beneath the ice, it would produce an induced magnetic field of a predictable strength and orientation, varying in a predictable way with Jupiter's rotation period. Kivelson's team ran the calculation. The observed signal matched. Galileo made 11 close flybys of Europa between December of 1996 and January of 2000. Some passed within a few hundred kilometers of the surface, close enough that the Moon filled a significant portion of the spacecraft's field of view, close enough that the magnetometer readings were clean and unambiguous rather than buried in the noise of distant measurement. Each additional flyby added data. Each new dataset was another opportunity to test the induced field hypothesis, to check whether the signal continued to vary in sync with Jupiter's rotation, to rule out alternative explanations. Kivelson's team used flybys where Europa was in different positions relative to Jupiter's field. If the ocean hypothesis was correct, the induced field should flip when Jupiter's field flipped, like a compass needle following a rotating magnet. It did, every time, without exception. Across multiple flybys, across different orbital geometries, across the full range of positions the spacecraft occupied around Europa. The paper Kivelson published in Nature in March of 1998 did not say, "We think there might be an ocean." It said the data was consistent with induction in a conducting layer, and that a liquid water ocean was the most plausible explanation for the observed magnetic signature. In scientific writing, that is about as direct as it gets. The ocean was there. The physics was speaking plainly. There was one problem. The magnetic signal was precise about certain things and completely silent about others. It could tell you that a conducting layer existed. It could constrain, roughly, how deep that layer began and how thick it was. What it could not tell you was the temperature of the water, the specific chemistry, the depth of the seafloor, or what, if anything, was happening at the bottom. It confirmed the ocean the way a sealed letter confirms that something is written inside. You know the letter exists. You know it has content. You have no idea what it says. And there was a second problem, sitting quietly beneath the first. The magnetic data argued for a global ocean. Global meaning it wrapped the entire Moon. Global meaning if the chemistry was right, if the energy budget was right, if the conditions were even approximately what tidal heating models predicted, it had been there for an enormously long time. Long enough for something to notice it. Long enough for something, given the right starting conditions, to do something with it. Whether those conditions existed, the magnetometer had no way to say. That question required a different kind of evidence entirely. Above Europa, above the ice and the silence and the long amber light, Jupiter waits. Its uppermost clouds are pale, almost white in places, the color of old cream, thin and high and cold, stretched into long bands by winds that have blown without stopping
since before this solar system had finished assembling itself. The bands are not sharp-edged. They blur at their margins, one color bleeding softly into the next, cream into the faintest yellow, yellow deepening slowly into amber, amber warming toward the burned rust of the lower latitudes, where the atmosphere thickens and the chemistry changes and the colors grow richer and heavier and more ancient feeling. Descending through those upper clouds would be a slow thing. The pressure increases gently, the way pressure does in deep water, not as a sudden weight, but as a gradual and total surrounding, the atmosphere thickening around you in increments too small to name individually, but unmistakable in their accumulation. The pale cream above gives way to amber. The amber deepens. The temperature shifts, colder first, then warmer as compression does its quiet work further down. The storms are visible from inside. Not dramatic from this vantage, not violent, not loud, just vast. A spiral of cloud the width of Earth turning slowly somewhere to the south, its edges dissolving and reforming on a timescale that makes patience feel like a small and human concept. The bands move in opposite directions on either side of it, sliding past each other in a shear that has been continuous for longer than the word continuous has existed. And below, deep in the amber dark, lightning. Silent from here. Each bolt lasting less than a second, but stretched across distances that would take a storm on Earth hours to cross. They flicker in clusters, then go still, then flicker again somewhere else. A slow, scattered conversation happening far below in a language made entirely of light. They have been doing this for 4.5 billion years. They will be doing it long after the ice on the moon above has had its question answered. The clouds close overhead. The amber deepens into rust. The pressure holds everything gently, firmly, with the indifferent comfort of something that does not know it is holding anything at all. The magnetic field evidence was indirect, elegant, rigorous, physically unambiguous, but indirect. The ocean had been inferred, not observed. And in planetary science, the distance between those two things matters enormously when you are trying to convince funding agencies to spend hundreds of millions of dollars on a spacecraft. What the field needed was something more visceral, something you could point at in an image and say, there, that is the ocean reaching the surface. That is the inside of this world touching the outside. In December of 2012, that something appeared. Lorenz Roth was a researcher at the Southwest Research Institute in San Antonio, working with data from the Hubble Space Telescope's Space Telescope Imaging Spectrograph, an instrument sensitive to ultraviolet light, wavelengths invisible to the human eye, but rich with chemical information. Roth and his team had been studying Europa's thin atmosphere, looking for signatures of water molecules being broken apart by radiation from Jupiter's magnetosphere. What they found in observations taken in November of 2012 was an excess of hydrogen and oxygen in the ultraviolet signal, and the excess was localized, not spread evenly across Europa's disk the way atmospheric processes would distribute it, concentrated near the South Pole. The most straightforward explanation was that water vapor was being vented into space from a specific location on the surface, a plume, or several, erupting from somewhere near the South Polar region, carrying material from below the ice and releasing it into the thin space above the surface. Roth's team published their findings in Science in December of 2013. The signal was real. It was also faint, right at the edge of what Hubble's instruments could reliably detect. And when follow-up observations were taken at different times, the excess signal wasn't always there. That inconsistency was immediately and justifiably flagged. Science does not take marginal detections at face value. It takes them seriously enough to look again with different instruments from different angles under different conditions. And in 2016, A team led by William Sparks at the Space Telescope Science Institute in Baltimore did exactly that. Sparks used a different Hubble instrument, the Advanced Camera for Surveys, and a different observational technique. Instead of looking for chemical signatures in ultraviolet light, his team observed Europa as it passed in front of Jupiter, using Jupiter's bright disk as a backlight. If plumes were erupting from Europa's surface and extending into space, they might appear as faint protrusions silhouetted against that backlight, physically visible structures, not just chemical signals. In 3 of 10 observations, they were there. Finger-like projections extending from Europa's limb, reaching up to 200 kilometers above the surface. Not present in every observation, not consistent in shape or location, but in those 3 passes, visible. Structures that matched, in scale and character, what active plumes would look like against a bright background. The paper landed in the Astrophysical Journal in September of 2016. 2 independent teams, 2 different instruments, 2 completely different observational methodologies, both pointing at the same conclusion. Europa appeared to be venting its ocean into space. The implications took a moment to land fully, and then they landed hard. If Europa was genuinely erupting material from its subsurface ocean, even intermittently, even from isolated locations, then the Europa Clipper mission had an opportunity that nobody had initially planned for. The spacecraft wasn't designed to land. It wasn't designed to drill. Getting through 20 kilometers of ice to reach the ocean directly was, and remains, a problem requiring technology and resources that don't exist yet in any funded mission. But flying through a plume is different. A spacecraft passing through an active plume could sample ocean material directly: water molecules, dissolved salts, organic compounds, whatever the ocean contains, without touching the surface at all. The ocean would be delivering itself to the instruments. The Clipper's mass spectrometer, designed to analyze particles and gases in Europa's environment, could in principle taste the ocean during a close flyby if the timing and geometry aligned. That possibility changed the conversation around what the mission might be able to answer. The honest version of where the plume evidence stands right now is this: the detections are real enough to take seriously, and inconsistent enough to remain unconfirmed. Subsequent Hubble observations have sometimes shown the signal and sometimes shown nothing. A reanalysis of old Galileo data published in 2018 by Shanja Jia at the University of Michigan found a magnetic and plasma disturbance in readings from a 1997 flyby that was consistent with Galileo having passed through an active plume without anyone realizing it at the time. The spacecraft wasn't designed to detect plumes. It may have flown through one and recorded the evidence in data that sat unexamined for 20 years. Nobody has fabricated anything here. Nobody is overstating the case. The plumes may be real and intermittent, erupting for days or weeks at a time and then going quiet, the way geysers on Earth follow cycles driven by subsurface pressure and temperature. Or the detections may be marginal artifacts of instruments pushed to their limits, finding signal and noise because the people looking had strong reasons to hope something was there. Europa Clipper will attempt to resolve this. Its instruments are more sensitive than anything Hubble carries for this kind of measurement. If plumes are active during any of the mission's close flybys, the spacecraft should detect them clearly and unambiguously. If it flies through 50 times and finds nothing, that will also be an answer. A quieter one, but an answer. For now, the plumes remain a held breath. The ocean below the ice may be announcing itself. The evidence says, probably. The science says, possibly. The spacecraft says, wait. While all of that was unfolding, the magnetometer readings, the Hubble detections, the decades of debate about ice thickness and plume consistency, a separate group of scientists was working with something much simpler: pictures. The Galileo spacecraft had returned photographs of Europa's surface in considerable detail during its 11 close flybys. And those photographs, studied carefully and at length, contained something that the magnetic field data and the ultraviolet spectrometry couldn't tell you. They contained color. Specifically, they contained color that shouldn't be there. Europa is an ice world. Ice, in the absence of contamination, is white. Gray-white, blue-white, the pale neutral tones of frozen water reflecting whatever light reaches it. That is what Europa's surface should look like if the ice were clean and undisturbed. It isn't. The cracks, the long linear features called linea that score Europa's surface in every direction, are dark. Brown and rust red and amber, colors running through the ice like something was dragged through it, or something leaked through it, or something from below worked its way up through every fracture the tidal flexing ever opened. Nobody put those colors there from the outside. Whatever stained the ice came from within. The question, sitting quietly in those photographs for years before the right instrument existed to answer it, was what exactly it was, and where exactly it came from. Because the answer to the second question pointed directly back to the ocean, and the answer to the first question pointed somewhere considerably more interesting than anyone had expected. The kind of detail that stays with you long after the night is over. A color in the ice, a signature from somewhere deep below. If you've drifted this far into the night with us, you're exactly who this channel was made for. A like helps us reach more people who need nights like this, and subscribing means the next quiet night already has something waiting in it. Now, about that rust and what it turned out to be. For years, the leading explanation for Europa's reddish discoloration was sulfur. Io, the innermost of Jupiter's 4 large moons, the most volcanically active body in the solar system, constantly erupts sulfur compounds into space. Some of that material gets swept up by Jupiter's magnetosphere and deposited across the surfaces of the outer moons. Europa sits close enough to Io's sulfur output that contamination from outside was a reasonable first hypothesis for the coloring. Sulfur compounds are reddish-brown. The geometry worked. The chemistry was plausible. It was also wrong, or at least significantly incomplete. In September of 2023, 2 researchers at Cornell University published an analysis of Europa observations taken by the James Webb Space Telescope. Samantha Trumbo and Michael Brown had been part of Europa's surface studies for years. Trumbo was a former graduate student of his who had spent her doctoral research on Europa's surface chemistry, examined Webb's near-infrared spectroscopy data with a specific question in mind. Carbon dioxide had been tentatively detected on Europa before by earlier instruments. Webb's sensitivity allowed them to map it properly for the first time. What they found was not evenly distributed carbon dioxide, not the signature of an ancient surface deposit sitting unchanged across the whole moon. It was concentrated, specifically concentrated in a region called Terra Regio, one of the most geologically active areas on Europa's surface, a zone where the ice has been disrupted and resurfaced relatively recently by the standards of planetary geology, where the tidal flexing of the crust has been most intense, where the surface is youngest and the connection to whatever lies below is presumably closest. The carbon dioxide was thickest exactly where you would expect it to be thickest if it had come from beneath the ice. This matters for a reason that requires a small detour into chemistry. Carbon dioxide does not persist on Europa's surface for long. Jupiter's radiation environment is hostile. The energetic particles continuously bombarding the surface break down chemical compounds relatively quickly on geological timescales. If carbon dioxide is sitting on the surface in detectable concentrations, it was put there recently. Not yesterday, but recently in the sense that planetary scientists use the word, meaning within the last few tens of millions of years, rather than the 4 billion year age of the moon itself. And carbon dioxide of the type Webb detected, the spectral signature, the specific absorption features in the infrared, is consistent with carbon that originated in a rocky, organic-rich environment, not carbon deposited by incoming comets or meteorites, not carbon from Io's volcanic output. Carbon that, in all likelihood, spent time in contact with Europa's rocky seafloor before working its way upward through the ice to the surface. The ocean floor has chemistry. That chemistry is reaching the surface. The two are connected. Trumbo described it carefully in the paper, noting that while the carbon dioxide surface origin in the ocean was the most straightforward interpretation of the data, the Webb observations alone couldn't fully rule out every alternative pathway. That is the appropriate scientific caution. The data is what it is. The interpretation is the most parsimonious one available. What she didn't say, but what the data implies, is this. Europa is not a sealed, static system. Material is cycling. The ocean is not simply sitting there, inert, behind a locked door. It is communicating with the surface, slowly, intermittently, through cracks and fractures and the slow convection of ice. And that communication leaves chemical fingerprints visible from 1 million miles away. Carbon dioxide is one fingerprint. The brown and rust-red streaking along the linea is likely another. Possibly magnesium sulfate, possibly sodium chloride, possibly a mixture of salts that precipitate when ocean water seeps into the cracks, reaches the surface, and has its volatile components boiled away by the vacuum. On Earth, when seawater evaporates in a tidal flat, it leaves a crust of salt behind. The same principle, operating on a world where the vacuum does the evaporating instead of the sun. There is something almost legible about it. A world that cannot speak, writing its composition on its own surface in the only language it has. Chemistry, color, the slow upward migration of whatever the ocean contains. The ocean has been trying to tell us what it is for a long time. We are only just learning to read it. Take a step back from the individual pieces and look at what has accumulated. A magnetic field disturbance detected by a spacecraft in 1996, explained only by a global saltwater ocean conducting electricity beneath the ice. Water vapor detected erupting from the South Pole by Hubble in 2012, and physical plume structures photographed in 2016. Carbon dioxide mapped by Webb in 2023, concentrated precisely where the surface is youngest and the ice most fractured, bearing the chemical signature of a rocky seafloor. Reddish streaks of salt running along every major fracture line, consistent with ocean water reaching the surface and leaving its minerals behind when the volatile components escape. 4 instruments, 3 decades, 2 space telescopes, and 1 orbiting spacecraft that wasn't even looking for most of this. All of it pointing at the same conclusion. Not toward a theoretical possibility, not toward a promising hypothesis that still needs its first supporting evidence, toward a specific place, a specific ocean, a specific body of water that is almost certainly there, and almost certainly has been there for a very long time. But here is the thing about accumulated evidence pointing at a conclusion. Pointing isn't arriving. The evidence tells us the ocean is real. It does not tell us what the ocean is like. It does not tell us what the water temperature is, what the pressure is at the seafloor, whether the chemistry is hospitable or corrosive, whether the tidal heating that keeps the water liquid also drives the kind of hydrothermal activity that could, in principle, power something more than chemistry. Those questions have an answer. The answer is sitting 485 million miles away, in the dark, under 20 kilometers of ice. And there is one number, one single figure that emerged from a completely different line of scientific inquiry, having nothing directly to do with Europa at all. That, when you hold it against everything this ocean might be, changes the weight of the question entirely. February 17th, 1977. The Pacific Ocean, 2,500 meters down. A submersible called Alvin, operated by the Woods Hole Oceanographic Institution in Massachusetts, was descending toward the Galapagos Rift, a section of the mid-ocean ridge system where two tectonic plates pull slowly apart from each other, leaving a seam in the ocean floor through which the interior of the Earth breathes upward. The three-person crew had been sent to look for hydrothermal vents, cracks in the seafloor where seawater seeps down into hot rock and comes back up superheated, carrying dissolved minerals. The vents had been predicted. Nobody had seen one yet. What they found changed the definition of life. The water was dark. The pressure was crushing. The temperature near the seafloor hovered just above freezing in most places, with superheated water jetting from the vent structures themselves. No sunlight had ever reached this depth, not once in the 4 billion-year history of the ocean. Every model of how life works assumed, at its foundation, that somewhere in the chain connecting any living thing to its energy source, there was the sun. Photosynthesis at the base, everything else built on top of it. The Galapagos Rift had not received that memo. Around the vents, in water that had never seen light, in darkness and pressure and heat that should have precluded biology by every assumption the field had worked from for a century, there was life. Tube worms 3 meters long, anchored to the vent structures in dense colonies, white and red and utterly alien. Crabs moving through the superheated plumes. Shrimp clustering in numbers that made the water appear to thicken. Clams, fish. Entire ecosystems, layered and complex and thriving, powered entirely by chemicals leaching from the Earth's interior, running on sulfur and hydrogen rather than sunlight, building food chains from the chemistry of rock rather than the energy of a distant star. Chemosynthesis, not photosynthesis. Life running on an entirely different fuel, in a place every prior model of habitability would have declared sterile. The biologist J. Frederick Grassel, who was part of the scientific team analyzing the Alvin observations, later described the discovery as the moment the study of life stopped being confined to the sunlit surface of a single world, because the underlying principle had been demonstrated to be far more flexible than anyone had imagined. The engine of biology capable of running on chemistry alone, in darkness and pressure and heat, without any reference to the star sitting 93 million miles above the ocean's surface. That was Earth. That was 1977. Now hold that discovery alongside what we know about Europa. Tidal heating from Jupiter flexing the rocky interior, continuously generating heat at the seafloor. A global ocean sitting directly on top of that rock, in contact with it for 4.5 billion years. If that contact produces hydrothermal activity, and the energy budget strongly suggests it does, and the geology of a tidally heated rocky seafloor in contact with liquid water makes it difficult to argue it doesn't, then the Galapagos Rift is not an Earth-specific anomaly. It is a template. And Europa, sitting 485 million miles from the sun, in the cold dark of the outer solar system, heated entirely from within, with more liquid water than Earth has ever held on its surface, may be running that template right now, in the dark, at the bottom of an ocean no one has ever seen. Europa is not alone. That is the fact. Simple, quiet, and when you hold it against everything science assumed for most of human history, genuinely staggering in what it means. Europa is not the only world in our solar system hiding a liquid water ocean beneath a frozen surface. It is not an anomaly. It is not the one exception that proves the rule that water is rare and Earth is special, and the conditions for life are a cosmic accident that happened once, here, and didn't happen anywhere else. Planetary science has now identified, through magnetometer readings, through gravitational measurements, through spectroscopy and flyby data, and decades of careful analysis, a minimum of 6 worlds in our solar system that almost certainly harbor subsurface liquid water. 6. Europa, yes, but also Ganymede, Jupiter's largest moon, the biggest moon in the entire solar system, carrying a subsurface ocean detected by the same magnetic induction method that found Europa's, confirmed by the Hubble Space Telescope in 2015, when Melissa McGrath's team at the SETI Institute observed the characteristic auroral rocking pattern that only a subsurface ocean could produce. Callisto, the outermost of Jupiter's large moons, showing similar magnetic induction signatures in Galileo data. Enceladus, Saturn's small, bright moon, which doesn't hide its ocean at all, but actively erupts it into space in continuous geysers of water ice and organic compounds that the Cassini spacecraft flew through repeatedly between 2005 and 2017, tasting salt and silica and hydrogen and complex organic molecules on every pass. Titan, Saturn's largest moon, where radar measurements from Cassini suggest a liquid water ocean beneath a crust of water ice, sitting below an atmosphere thick with organic chemistry. And Mimas, Saturn's small, heavily cratered moon, the one that looks unsettlingly like a certain fictional space station, where gravitational measurements published in 2024 by Valerie Laney at the Paris Observatory suggest a young, recently formed ocean beneath the surface that nobody expected to find there at all. 6 worlds, around one star, in one solar system. The assumption that Earth was the rare accident, the one place where the conditions aligned, where water stayed liquid, where the distance from the sun and the geological luck and the atmospheric chemistry happened to combine into something habitable, that assumption has been revised so completely it is nearly unrecognizable. Liquid water, the one ingredient historically considered most fragile and most unlikely to persist beyond our own world, turns out to be one of the more common things the solar system produces. We are not living at an oasis in a desert. We are, it seems, in a place with water on every side, most of it hidden, most of it dark, most of it utterly unknown. But there. Let that sit for a moment. 6 worlds, one star, and those are only the ones we've found so far, in a solar system we've been studying seriously for less than a century, with instruments that are still in their early generations. The number is almost certainly an undercount. What this does to the question of life in the universe is not a small adjustment. It is a fundamental reorientation. For most of the history of science, the working assumption was that Earth was the exception, that the specific combination of distance from the sun, planetary size, geological activity, and liquid water that produced a habitable world was so unlikely that it probably hadn't happened anywhere nearby, and might not have happened anywhere else at all. That assumption drove the Fermi paradox. If life is possible, where is everybody? Because it began from a place of assumed rarity. The rarity was in the wrong place. It wasn't water that was rare. It wasn't energy that was rare. It wasn't even the chemistry, carbon, hydrogen, oxygen, nitrogen, the building blocks of every living thing we've ever found are among the most abundant elements in the universe. What was rare was our ability to look far enough and carefully enough to see what was already there. Of those 6 ocean worlds, Europa remains the most compelling candidate for a closer look. Not because it is the largest ocean, or the warmest, or the most chemically rich in any confirmed sense, but because of a specific combination of factors that no other world currently matches. The ice shell, while thick by human engineering standards, is the thinnest of any confirmed subsurface ocean in the solar system. The tidal heating is intense enough to almost certainly drive seafloor activity. The surface chemistry, the carbon dioxide, the salt deposits, the possible plumes, suggests active exchange between ocean and surface rather than a sealed, static system. And it is, in the grand geography of the outer solar system, relatively accessible. Jupiter is closer than Saturn. Europa's flybys are achievable with technology that exists right now, in a spacecraft that launched 6 months ago and is already on its way. The others are extraordinary. Enceladus, with its continuous geysers, may actually be easier to sample in one sense. The ocean delivers itself to space without any ice to penetrate. But Enceladus is small, its ocean potentially shallow, its long-term habitability less certain. Europa has the ocean, it has the energy, it has the chemistry signatures, and now it has a spacecraft coming. Whether the ocean has anything else, anything that moves, anything that metabolizes, anything that in 4.5 billion years of warmth and water and chemistry has done what chemistry sometimes does when given enough time and the right conditions. That is the question the Clipper mission cannot answer. That question requires a lander, and the lander does not yet exist. Below the frost and the cracked plates and the long amber light of Jupiter, below the rust-colored streaks and the ancient ridgelines and the thin aurora threading along the southern horizon, there is darkness. Not the darkness of a room with the lights off, or a night without a moon, or the deep of a forest at the wrong hour. Those darknesses have texture. They have the memory of light in them, the knowledge that morning exists, the sense that somewhere just beyond what the eye can reach, the world continues in its ordinary colors. This darkness has none of that. It is the darkness of a place where light has never been, where no photon has ever arrived and been absorbed and scattered and carried upward and outward in the long chain of illumination that connects every lit thing to every other lit thing. The ice above seals it completely. 20 kilometers of frozen water pressing down in total silence. And beneath that seal, the ocean simply holds itself in the dark, patient and complete, needing nothing from the universe above. The water is cold near the top. Not frozen, just cold. The deep and heavy cold of water that sits far from any source of warmth, that has been at this temperature for longer than the concept of temperature has existed anywhere that could conceive of it. It rests against the underside of the ice the way still water rests against any ceiling, pressing gently, going nowhere, in no hurry to be anywhere else. Deeper, something changes. The cold gives way by degrees, slowly, over distances that take time to cross even in the imagination. The water warms. Not to comfort, not to anything a human body would recognize as warmth, but perceptibly, measurably, in the way that deep places sometimes hold the memory of heat, even when the surface has long forgotten it. The warmth rises from below in slow columns, lazy and unhurried, carrying dissolved minerals from the rock beneath, threading upward through the dark in the way smoke rises through a still room, without urgency, without destination, simply following the physics of warm things moving through cool ones. The seafloor is somewhere below, rocky and old and dark, dusted with the slow accumulation of whatever settles downward through 4.5 billion years of ocean. It breathes upward in its own way, heat and chemistry and the slow exhale of a world working quietly in the dark, doing what worlds do when no one is watching, which is the same thing they do when someone is. The silence here is not empty.
It is full of pressure, full of the slow movement of water in total darkness, full of the weight of ice above and rock below, and the vast, cold, middle distance between them. A silence that has been accumulating since before the first living thing on Earth drew its first breath, that has continued without interruption through every age of our world's history, that is still accumulating now, in this moment, while the surface above it reflects Jupiter's light into space, and the spacecraft, moving toward it, crosses another 1,000 kilometers of the long, dark. And the ocean holds its silence, deep below the ice. It always has. It is in no hurry to stop. On the 14th of October 2024, a Falcon Heavy rocket lifted off from Launch Complex 39A at Kennedy Space Center in Florida and carried into space the most expensive planetary science spacecraft NASA has ever built, Europa Clipper. 6,000 kilograms, 9 science instruments, a solar panel array spanning 30 meters tip to tip, the largest ever deployed on a planetary mission. Necessary because at Jupiter's distance from the Sun, solar energy arrives at roughly 4% of Earth's intensity. And the spacecraft needs every square centimeter of collection area it can carry to power its instruments through a decade of operation. The launch had been delayed from its original window. The rocket had been changed. The budget had been debated and revised and debated again across nearly 2 decades of planning and politics and competing priorities within NASA's science portfolio. It left the ground on schedule. And when the Falcon Heavy's upper stage released it, and it unfurled those enormous panels against the black, engineers in the mission control room at JPL, who had spent 15 years building toward that moment, watched the telemetry confirm successful deployment and, by most accounts, said very little. Some things are too large for the room they happen in. The mission design is a solution to a problem that has no elegant answer. Jupiter's radiation environment is among the most hostile in the solar system. The planet's powerful magnetic field traps high-energy particles, electrons and protons, accelerated to near relativistic speeds in radiation belts that surround Jupiter and extend through the orbits of its inner moons. Europa sits deep inside those belts. A spacecraft orbiting Europa would absorb a radiation dose equivalent to roughly 5,400 gray per day, a unit of absorbed radiation energy. For context, a dose of around 5 gray is lethal to a human being. 5,400, delivered continuously, would destroy most spacecraft electronics within a matter of weeks. You cannot orbit Europa, not for long, not with any instrument package sophisticated enough to do the science the mission requires. The solution is to not orbit Europa at all. Europa Clipper will orbit Jupiter on a long, looping path that takes it far out of the radiation belts between encounters, exposing the spacecraft to Jupiter's harshest radiation only during the relatively brief periods when it dips close to Europa for each flyby. The spacecraft will complete roughly 50 close passes of Europa over the course of the mission, each one lasting only a few hours near closest approach, each one collecting as much data as the instruments can gather during that window before retreating back out to the relative safety of a more distant Jovian orbit. It is an ungainly solution in some ways. Each flyby is a sprint, instruments powered up, data collected at maximum rate, then the spacecraft pulls away and the team waits weeks or months for the next pass. But it is the solution physics allows. And 50 flybys, spread across a range of orbital geometries, altitudes, and lighting conditions, will collectively build a picture of Europa more detailed and comprehensive than anything produced in the entire history of planetary science to date. 9 instruments. Each one answers a specific question the previous generation of missions left open. The magnetometer, built by a team that includes scientists who worked on the original Galileo instrument, carrying forward Kivelson's legacy directly, will measure Europa's induced magnetic field with far greater precision than Galileo achieved. It will constrain the ocean's depth, its salinity, and the thickness of the ice shell more tightly than the 1998 estimates allowed. The ice-penetrating radar, called REASON, Radar for Europa Assessment and Sounding, Ocean to Near Surface, will send radio waves through the ice and listen for the reflection from the ocean below. If the ice shell has internal structures, lakes, fractures, channels where ocean water has worked its way upward, the radar will map them. If the shell is thin in places, REASON will find those places. The mass spectrometer will analyze the composition of Europa's thin atmosphere and any plume material the spacecraft encounters during close passes. It can detect organic compounds, salts, and gases at extraordinarily low concentrations, low enough that even a brief passage through a dilute plume should yield usable chemical data. The thermal imager will map surface temperatures, looking for warm spots that might indicate places where heat from below is reaching the surface, possible sites of recent geological activity, possible locations of thin ice. Together, the 9 instruments will not answer the question of whether something lives in Europa's ocean. That is not what they were designed to do. They were designed to tell us whether something could, to characterize the ocean with enough precision that the next mission, the lander, if and when it is funded and built and launched, will know where to go and what to look for when it gets there. Europa Clipper is expected to reach Jupiter in April of 2030. Its first Europa flyby is scheduled for shortly after orbital insertion. The primary science mission runs through 2034, with the possibility of an extended mission beyond that, depending on spacecraft health and fuel reserves. The scientists who proposed this mission in the early 2000s will be deep into their careers, many into retirement, when the data starts arriving. Several of the graduate students who cut their teeth on Galileo flyby data are now senior researchers leading instrument teams on the Clipper. The work passes between generations the way all long science does, each cohort carrying it a little further, handing it forward to someone younger who will carry it further still. Margaret Kivelson, whose magnetometer data started all of this in 1996, was 86 years old when Europa Clipper launched. She watched it leave the ground. Far ahead of Jupiter, sharing its long path around the Sun, a population of ancient rocks drifts in loose congregation through the dark. They are called the Trojans, thousands of them, perhaps hundreds of thousands, gathered in the gravitational balance points that trail and precede Jupiter in its orbit, held there by the competing pulls of Jupiter and the Sun, the way a bead of water holds its place in the shallow curve of a bowl. They have been there since the solar system was young. Some of them are among the oldest surfaces in existence, unchanged, unweathered, untouched by anything except the occasional slow collision with a neighbor and the patient, continuous arrival of sunlight, too faint to warm them by any measure a human body would register. They tumble slowly, not dramatically, not the violent spinning of something newly disturbed. The slow, thoughtful rotation of objects that have been turning at the same rate for 4 billion years and see no reason to change. A rocky face catches the distant sun and holds the light for a few hours,
pale and flat and mineral, then turns away and returns to shadow. Iron and olivine and carbon black silicate, the colors of the very earliest chemistry, the palette of a solar system that had not yet decided what it was going to become. The spaces between them are enormous. This is not the crowded asteroid belt of science fiction, rocks jostling for position in a narrow, dangerous band. The Trojans are spread across a volume so large that if you stood on one and looked in every direction, the nearest neighbor might be invisible, too small, too dark, too far to find without instruments. The darkness between them is clean and uncluttered, a deep and comfortable distance that has no particular quality except its patience. Sunlight reaches them slowly. It left the sun 8 minutes ago when it touched your face on Earth. Here it arrives 43 minutes after departure, diluted by distance, softer and cooler, and carrying less of the urgency that sunlight on a warm afternoon seems to possess. It falls across the surfaces of these rocks without warming them, illuminates them without animating them, touches them and passes and continues outward into the deeper dark beyond. Nothing here has changed since before the first cell divided in the first warm pool on the early Earth. Nothing here is in any hurry. The ocean holds its silence deep below the ice. And out here, among the old rocks turning in the faint light, the silence holds too. A different silence, colder and more open, but made of the same patient darkness, the same indifference to time, the same quality of a universe that has been here long before the question and will be here long after the answer. There is a disagreement in Europa science that has been running for roughly 30 years, and it has not been resolved yet. It concerns the ice. Specifically, how much of it there is, and what that amount means for everything else the mission is trying to understand. The question seems straightforward. How thick is Europa's ice shell? Measure it, settle it, move on. But measuring the thickness of an ice layer on a moon 485 million miles away from instruments that have never been closer than a few hundred kilometers to the surface turns out to be considerably harder than it sounds. The Galileo magnetometer data constrain the depth at which the conductive ocean layer begins, but with enough uncertainty in the measurement that the answer could fall anywhere across a wide range. Gravity measurements from Galileo helped narrow the moon's internal structure, but couldn't distinguish between a thin shell and a thick one with the precision the debate required. So the question stayed open. And into that open question, two camps moved. The thick shell model holds that Europa's ice is deep, 20 to 30 kilometers throughout, possibly more in some regions. Proponents of this view, including Paul Schenk at the Lunar and Planetary Institute in Houston, point to the surface geology as their primary evidence. Europa's surface shows features called lenticulae, small rounded domes and depressions scattered across the plains, typically a few kilometers across. The thick shell interpretation explains these as the surface expression of a process called convection, happening deep within the ice itself. Convection in ice works the same way it does in any material that is warm at the bottom and cold at the top. The warmer, softer ice near the ocean interface is slightly less dense than the cold, brittle ice near the surface. It rises slowly, over tens of thousands of years, in slow churning columns, the way wax moves in a lava lamp, carrying heat upward from the ocean and releasing it near the surface before cooling and sinking again. When one of those rising columns reaches shallow depth, it can cause the surface to dome upward slightly. When it subsides, it can leave a depression. This process, if it operates throughout a 30-kilometer ice shell, keeps the ice mechanically isolated from the ocean. Material from the ocean can work its way upward through convection, which is consistent with the carbon dioxide and salt detections, but the journey is slow, indirect, and the ocean remains fundamentally sealed from the surface for long periods. The thin shell model argues something more dramatic. Richard Greenberg at the University of Arizona spent years developing the competing view, which holds that Europa's ice may be only a few kilometers thick in some regions, possibly thin enough in places that tidal flexing, the same force that heats the interior, periodically cracks the shell entirely, opening transient windows directly from the ocean to the surface. The evidence Greenberg and colleagues point to includes the linea themselves, those long, rust-colored fracture systems that cross Europa's surface in sweeping arcs and double ridges. The double ridge structure specifically is difficult to explain convincingly in a thick shell model. One mechanism that produces double ridges naturally is the repeated opening and closing of a crack that reaches all the way to the ocean, tidal forces pulling it apart during one part of Europa's orbit, pressing it shut during another, with ocean water welling up into the gap each time it opens and freezing there, building the ridge walls incrementally with each tidal cycle. If that mechanism is correct, the surface of Europa is not just a passive lid sitting on top of the ocean. It is actively, continuously exchanging material with it. Every tidal cycle, every 3.5 days, some portion of the surface cracks open and briefly connects to the water below. The implications for habitability are significant. A thin, actively cycling ice shell means oxidants produced at the surface by Jupiter's radiation, hydrogen peroxide, oxygen, sulfate compounds, are being continuously delivered into the ocean. On Earth, oxidants are essential to the kind of complex metabolic chemistry that powers most life. If Europa's ocean is receiving a steady supply of surface-produced oxidants through a thin, permeable ice shell, its chemical energy budget looks considerably more interesting than a sealed, static ocean would. Neither camp has won this argument. Both interpretations are consistent with the available data, each explaining some surface features more elegantly than the other, while struggling with different aspects of the geology. The Galileo data wasn't precise enough to settle it. Telescope observations from Earth lack the resolution. Hubble can tell you what chemicals are on the surface, but not how deep the ice goes beneath them. This is precisely the problem Europa Clipper's Reason radar was built to solve. Ice-penetrating radar works by sending radio waves through a medium and listening for the reflection from the boundary where one material meets another. In this case, where ice meets liquid water. The technique is well established. It has been used to map the subglacial lakes beneath Antarctica's ice sheet from aircraft flying overhead. Applied from a spacecraft at 25 kilometers altitude, making repeated passes over different regions of Europa's surface, Reason should be able to measure the ice thickness directly, not infer it from surface features or gravity models, but measure it, the way you measure anything, by sending a signal in and reading what comes back. The first passes will produce the first real numbers. Those numbers will either confirm one of the two existing models, require a third, or, and this is not unlikely in planetary science, reveal something neither camp anticipated. The ice may not be uniformly thick or uniformly thin. It may vary across the surface in ways that the global models didn't fully account for. Thick over ancient stable regions, and thin where tidal activity has been most recent and most intense. The answer is in the ice. The radar is on its way. Consider two oceans. Both are liquid water. Both are global, one wrapping the surface of a planet, one wrapping the interior of a moon. Both are dark at their deepest points, dark enough that no light from any star has ever reached the floor. Both sit on top of rock. Both have been there in some form for billions of years. On paper, the similarities are striking. In practice, the differences run very deep. Earth's ocean has a surface. That seems obvious, unremarkable even, until you consider what having a surface means for an ocean's chemistry and character. A surface means contact with the atmosphere. It means rain falling in from above, carrying dissolved gases and minerals from the continents. It means sunlight penetrating the upper layers, driving photosynthesis, powering the base of a food chain that eventually reaches every living thing in the water. It means weather, storms churning the upper layers, redistributing nutrients, keeping the chemistry in constant motion. It means evaporation and the water cycle, and the continuous exchange between ocean and atmosphere and land that has been running without interruption since Earth first had all three. Earth's ocean is connected to everything. Europa's ocean is connected to nothing. It has no surface in any meaningful sense, only a ceiling, 20 kilometers of ice pressing down from above, sealing the water from any contact with the space beyond. No rain falls into it. No sunlight reaches it. No atmosphere sits above it to exchange gases with it. It has been sealed, as far as the science currently suggests, for most of the 4.5 billion years it has existed. A closed system running entirely on its own internal chemistry, powered entirely from below, with no input from the universe outside the ice except the tidal forces that keep it liquid. There is a word for what Europa's ocean is in the language of ecology. It is an endolithic environment, a system that derives its energy entirely from within the rock it sits on, sealed from external energy sources, self-contained. On Earth, endolithic ecosystems exist. They are found inside rocks, in deep mines, in ancient aquifers that haven't connected to the surface in millions of years. They are small, slow, and sparse. They survive on almost nothing, and they survive. There is one more comparison worth sitting with. Earth's deep ocean was not discovered until 1977. That is not a typo. The planet's own ocean, covering 70% of its surface, holding 97% of its water, the largest and most accessible body of liquid on the world, was not fully explored in its deepest regions until a submersible descended to the Galapagos Rift and found life where no model predicted life could exist. The ocean was there the entire time. Humans simply hadn't looked. Europa's ocean has been there for 4.5 billion years. We found it, or rather, we felt its magnetic presence, in 1996, using instruments on a spacecraft that was built to study something else. We have not yet been within 25 kilometers of its surface. We have not touched the ice above it. We have not sent anything capable of reaching the water itself. Everything we know about Europa's ocean, we know from the outside. Every ocean on Earth that has ever been explored directly has contained life. Not some of them, not most of them, every one. Hot vents, cold seeps, pitch-dark abyssal plains, hypersaline pools at the bottom of the Mediterranean. Everywhere water has collected in volume on this planet and been examined with any instrument capable of detecting biology, something biological has been found.
That pattern is not a guarantee. It is not a scientific argument that Europa must contain life. Life may have specific requirements we don't yet fully understand, requirements that Earth meets everywhere and Europa meets nowhere. The ocean below the ice may be extraordinarily well suited for chemistry and extraordinarily poorly suited for biology. Nobody knows. But the pattern is there, and the ocean is there, and the two facts sitting next to each other in the quiet of this particular night refuse to stay entirely separate. Habitability is a careful word. Scientists use it specifically, and the specificity matters. A habitable environment is not an environment that contains life. It is an environment that could support life, one that meets, as far as we can determine, the minimum conditions biology requires. The distinction is not semantic. It is the difference between a question we can currently investigate and a question we cannot yet answer at all. The conditions for life, as science understands them, reduce to three requirements: liquid water, a source of chemical energy, and the right chemistry. Specifically, the availability of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur in forms that biology can work with. These are the ingredients. They are not by themselves life, but without them, nothing we have ever called life has managed to exist. Europa almost certainly has all three. That sentence deserves its qualifier, almost certainly. Not confirmed, not proven beyond the remaining uncertainties, but supported by converging evidence from multiple instruments across multiple decades to a degree that most planetary scientists consider the basic habitability case reasonably solid. The liquid water is there. The tidal heating provides energy. The carbon signatures Webb detected and the salt compounds reaching the surface suggest the right chemical elements are present and cycling. On those three counts, Europa passes the basic test. But passing the basic test and being genuinely habitable are not the same thing. In 2023, Lini Quick at NASA's Goddard Space Flight Center published a modeling study examining the energy budget of Europa's ocean, specifically how much chemical energy might be available at the seafloor if hydrothermal activity is occurring at a rate consistent with the tidal heating estimates. The conclusion was that the available energy could, in principle, support a biomass comparable to what exists in Earth's deep ocean hydrothermal ecosystems. That is an encouraging number. It is also a number built on a stack of assumptions, each one reasonable, but none of them confirmed by direct measurement. The model assumes hydrothermal activity is occurring. The model assumes the chemistry at the seafloor includes the right compounds in the right concentrations. The model assumes the ocean is well enough mixed that energy and chemistry are distributed rather than concentrated in a few isolated hotspots surrounded by inert water. Quick was careful to state the uncertainty range explicitly. The estimate spans several orders of magnitude. The actual biomass Europa's ocean could support, if it supports any at all, could be considerably higher than Earth's deep ocean ecosystems, or considerably lower, or zero. Nobody is overstating the case here. The point of the paper was not to claim Europa harbors life. The point was to demonstrate that the energy budget is not obviously prohibitive, that the ocean is not, on energetic grounds alone, ruled out as a habitat. That is a more modest claim than it might sound, and it is the appropriate claim given what the data currently supports. The honest inventory of what we don't know about Europa's ocean is longer than the inventory of what we do. We don't know the pH of the water. An ocean that has been in contact with the rocky seafloor for 4 billion years, with volcanic activity introducing sulfur compounds and carbon dioxide and other acidic gases, could in principle have drifted toward conditions more corrosive than anything biology would tolerate. Or it could be broadly neutral, or mildly alkaline. Models suggest a range. None of them can be tested without a measurement. We don't know the specific temperature at the seafloor. Tidal heating estimates produce a range, from barely above freezing throughout to locally very hot near active vent structures. The difference matters enormously for chemistry and for biology. Life on Earth clusters around hydrothermal vents not because heat alone is hospitable, but because the temperature gradient between the hot vent fluid and the cold surrounding water drives the chemical reactions that power the base of the food chain. Without that gradient, the energy budget collapses. With it, life flourishes. We don't know whether oxidants from the surface are reaching the ocean in meaningful quantities. The thin shell model suggests they are, cycling down through cracks and convection. The thick shell model suggests the delivery is slow enough that the ocean may be chemically reducing, dominated by hydrogen and sulfur rather than oxygen compounds, which would make it habitable only to a specific class of anaerobic chemosynthetic organisms, if anything at all. We don't know whether the ocean has been continuously liquid. The models strongly suggest it has been. Tidal heating has presumably been operating since Europa formed, and the mathematical case for an uninterrupted ocean over geological time is solid. But models are models. A past catastrophic event, a period of reduced tidal heating due to orbital changes, a temporary freezing of the entire ocean. These scenarios are considered unlikely, but unlikely is not impossible. And a freezing event that killed everything and was followed by remelting would reset the biological clock entirely. What we know, genuinely, measurably, from instruments that have actually been to Jupiter, is that the ocean is almost certainly there, that the chemistry is cycling, and that the energy budget is not ruled out. What we don't know is everything else. There is a particular kind of scientific honesty that is harder to maintain than it sounds. It is the honesty of saying, we have strong reasons to be interested in this place, and we do not yet have the data to know whether our interest is justified. It requires resisting the pull of the compelling story, the ocean, the vents, the 4 billion years, the 6 worlds, and holding open the possibility that Europa's ocean is a cold, dark, sterile body of water that has never contained anything more complex than dissolved minerals and will not contain anything more complex when we finally reach it. That possibility exists. It is not the most exciting outcome. It is scientifically a legitimate one. The Clipper mission will not answer it. It will narrow the uncertainty. It will tell us whether the ice is thin or thick, whether plumes are real, whether the magnetic field is consistent with a salty and therefore potentially habitable ocean. It will map the surface chemistry with unprecedented detail and give the scientists who will design the next mission, the lander that doesn't yet exist, the information they need to choose a landing site wisely. The answer to the actual question, is anything alive in that ocean, waits for a different machine, a different budget, a different decade. For now, the ocean sits in the dark, 485 million miles away, neither confirming nor denying anything, holding its silence with the complete indifference of a place that has never been asked a question before and doesn't know one is coming. Somewhere far from here, in a part of the galaxy where no sun yet burns, a cloud of gas and dust holds itself in the dark. It is enormous, not the smallness of a moon or a planet or even a solar system, but the vast, diffuse enormousness of something measured in light years. Something so large that the concept of an edge feels approximate, a gradual thinning rather than a boundary.
the cloud becoming space by degrees rather than all at once. It is cold, colder than Europa's surface, colder than the space between the Trojan rocks, colder than almost anything that the word cold is usually asked to describe. The molecules inside it move so slowly that chemistry here operates at a pace that makes the word slow feel inadequate. And yet something is happening. Gravity is patient. It does not announce itself. It does not rush. It works at the pace of accumulation, each particle drawing every other particle toward it by an amount so small it cannot be measured in any unit a human body has ever experienced. And yet adding, always adding, the pool increasing as the density increases increasing as the pool increases. A slow and certain tightening that has been underway since this cloud first condensed from the larger nothing around it. In the deepest part of the cloud, the gas is denser. The dust gathers in dark threads, fine and cold, drifting toward the center of whatever gravitational seed first drew them inward. The threads thicken into filaments. The filaments pull toward each other with the same imperceptible patience. At the very center, a knot of matter forms, not dramatically, not suddenly, but with the unhurried certainty of something following physics the way water follows a slope, because there is simply nowhere else for it to go. The knot grows denser. The pressure inside it builds. Around it, a disk of remaining gas and dust spreads slowly outward, turning in a flat spiral, material that did not fall all the way inward but found its orbit instead and circles in a slow ring, cooling, thickening, clumping in places where the density briefly tips past a threshold and one piece of matter finds itself slightly more attractive than the space around it. Those clumps will become worlds. Some of them will be cold. Some will be frozen through and through, dark bodies tumbling in the outer reaches of whatever solar system this cloud becomes, never warmed enough to know the difference between solid and liquid. And some of them, the ones close enough to the warmth, or the ones lucky enough to be squeezed from the inside by the gravity of something larger nearby, will find in their interiors a heat they did not expect. And in that heat, somewhere, something will melt. The ocean holds its silence deep below the ice. It began here, or somewhere like here, in a dark cloud too cold and too vast and too patient for any of the urgency that came later. In the slow fall of dust toward a center, in the compression of rock around a heat that had nowhere else to go, in the long, quiet chain of physics that connects a molecular cloud to a cracked and frozen moon lit by the amber light of a gas giant, carrying within it a body of dark water that has been waiting, without knowing it is waiting, for as long as waiting has existed. Everything we've covered tonight now sits inside a container with a lid that hasn't been opened yet. The magnetic field evidence, the Hubble detections, the carbon dioxide mapped by Webb, the salt deposits running along every fracture line, the ice shell debate still unresolved after 30 years, the 6 worlds, the hydrothermal vents on Earth and what they changed about the definition of possible, the Clipper mission already in transit, already crossing the long dark between here and Jupiter, carrying 9 instruments
and the accumulated patience of several generations of scientists who spend their careers building toward a question they may not live to hear answered. All of it contained, all of it waiting. The spacecraft will arrive at Jupiter in April of 2030. It will begin its flyby sequence. It will send back data that no instrument has ever collected about Europa. Measurements precise enough to settle questions that have been open since 1996. And those measurements will either confirm what the models predict, or they will do what data has a habit of doing when it finally arrives after a long wait. They will be stranger and more complicated and more interesting than anyone expected. And the questions will multiply rather than resolve. And the scientists who receive them will spend the next decade arguing about what they mean. That is how it goes. That is how it has always gone. From Galileo Galilei noting 3 small points of light in his journal on a January night in 1610, to Margaret Kaivelson staring at a magnetic anomaly in 1996, to Samantha Trumbo mapping carbon dioxide on a frozen moon from a telescope that sees in wavelengths the human eye cannot detect. The question sharpens. The instruments improve. The answer gets closer without ever quite arriving, because every answer in science is also an opening, and the openings keep getting more interesting the further in you look. Somewhere under the ice, if the ocean is what we believe it to be, the answer to one of the oldest questions humanity has ever formed sits in the dark, patient and complete, with no knowledge that anyone is coming. It has been waiting 4.5 billion years. A few more won't trouble it. There is something worth sitting with at this point in the night. Not a fact, not a discovery, not a measurement waiting to be made. Something older than any of those things. Something that was present before the first telescope, before the first calculation, before the first person looked up at Jupiter burning steadily in the night sky and wondered, even vaguely, what it was. The act of looking. Humanity has been asking whether it is alone in the universe for as long as there have been humans capable of forming the question. Every cosmology constructed by every culture that left a record made some attempt at the answer. Placed beings in the sky, or denied that the sky contained anything worthy of the name, or imagined the stars as the fires of distant worlds occupied by distant minds. The question predates science by tens of thousands of years. It may predate language. It may be as old as the first mind that looked up on a clear night and felt the specific unease of not knowing whether the darkness looked back. Science inherited that question and did something the prior traditions couldn't. It made it specific enough to test. Not, are we alone in the universe? A question so vast it resists every instrument ever built. But, is there liquid water on this particular moon? Is the magnetic field consistent with a conducting layer beneath the ice? Is the carbon dioxide in this specific region of the surface consistent with a rocky seafloor origin? One small, precise, answerable question at a time. Each one a single step along a path that has been walked now for 400 years without reaching its end. The thread from Galileo Galilei to the Europa Clipper mission is unbroken. It passes through Stanton Peele doing tidal heating calculations at Santa Barbara in 1979, through the engineers at JPL arguing about trajectory designs through most of the 1980s, through Margaret Kivelson at UCLA
spending 2 years making sure the magnetic anomaly was real before she put her name on it. Through Lorenz Roth at the edge of what Hubble could detect in 2012. Through Samantha Trumbo mapping carbon in infrared wavelengths on a telescope that didn't exist when Kivelson published her paper. Each of them was asking the same question at a finer resolution than the one before. Each of them handed something forward, a number, a method, a constraint, a named phenomenon, that the next person needed in order to go one step further. This is not unique to Europa science. It is how all long science works, the way all long human things work. Each generation receiving something incomplete from the one before and making it slightly less incomplete before passing it on. But there is something about this particular chain of inquiry, 4 centuries long, aimed at a point of light that Galileo noted in a journal without knowing what it was, that makes the continuity feel more deliberate than it is. It isn't deliberate. Nobody planned it. Galileo Galilei wasn't thinking about subsurface oceans when he wrote down those 4 small points of light in January of 1610. He was thinking about the motion of bodies in the sky, about the argument he was building against a cosmology that placed Earth at the center of everything. He was wrong about the center. The cosmos has no center, or every point in it is the center, depending on how you look. But the moon he noted, the second one from Jupiter, the small one, turned out to be one of the stranger and more significant places in the solar system. And the act of noting it started a thread that 414 years later is still being pulled. There is something in that continuity that resists easy description. Not pride exactly, though pride is part of it. Not wonder exactly, though wonder is there too. Something more like recognition, the feeling of seeing a very long line of people all looking in the same direction, across a span of time too large for any one of them to have witnessed, all of them contributing their small, precise increment to a question none of them will fully answer. And the question's still open, and the ocean's still there. And somehow, both of those facts feel like exactly the right outcome for a night like this. Rise above it all, above Europa, above Jupiter, above the flat plane of the solar system, where the planets orbit in their slow, concentric rings around an ordinary star. Rise until the sun itself diminishes, not dramatically, not in a rush, but steadily, the way a light dims when you walk away from it down a long corridor, becoming smaller and cooler and less insistent with every step until it is simply one light among many, indistinguishable from its neighbors, a warm point in a field of warm points that stretches in every direction without end. Rise until the galaxy comes into view. It is a flat thing seen from above, not the edge-on band of the Milky Way that a dark sky night reveals from Earth's surface, that pale river of crowded light running from horizon to horizon, but the whole shape of it, seen from outside, from the high, cold dark of the galactic halo, where the ancient globular clusters drift in their long, slow orbits, like cities that predate the galaxy they circle. The spiral is faint from here, soft-edged, not the crisp, defined arms of the astronomical photographs taken by instruments that gather light for hours, just a gentle, luminous smear, a slow wheel of 400 billion stars turning in a silence so complete and so enormous that the concept of sound becomes difficult to hold on to. The arms wind outward from a central brightness, diffuse and gradual, their edges dissolving into the sparse field of stars that surrounds them the way a whisper dissolves into a quiet room. Not stopping exactly, just becoming indistinguishable from the surrounding stillness. The globular clusters drift below, between the halo and the disk. Ancient things, some of them as old as the universe itself. or nearly. Dense, spherical swarms of hundreds of thousands of stars, each cluster a city that formed in the first billion years of cosmic time and has been orbiting the galaxy ever since, outlasting everything that has risen and fallen inside the disk below. They move in long, slow ellipses, dipping down through the galactic plane and rising again on the other side, tracing paths that take hundreds of millions of years to complete. They have been doing this since before the sun existed. They will be doing it long after. From here, the solar system is invisible. The sun is somewhere in the middle distance, roughly 2/3 of the way from the galactic center to the outer edge of the disk, in a quieter region between two spiral arms where the stellar density is moderate and the cosmic neighborhood has been stable enough, for long enough, that complicated chemistry had time to do complicated things on at least one small rocky world orbiting it. But from the halo, none of that is visible. The sun is a point. Its planets are far too small and far too dark to find without knowing exactly where to look. The moon, orbiting Jupiter, the small one, the second from the gas giant, the one with the cracked ice and the dark ocean and the faint aurora threading along its southern horizon, is invisible from here, dissolved into the general glow of one ordinary star among 400 billion. And yet, the ocean is there, sealed and silent and patient in the dark beneath the ice, warm near the floor where the rock breathes upward, cold near the ceiling where the ice presses down, vast and still and completely indifferent to the distance between itself and anything that might be curious about it. The ocean holds its silence deep below the ice. From here, from this high, cold place above the slow wheel of the galaxy, everything holds its silence. The globular clusters in their ancient orbits, the spiral arms winding their slow way around a center that has been turning since before the first star burned. The halo itself, sparse, enormous, patient, full of things that have been here since the beginning of what here means. A silence so old, it has no memory of ever being anything else. And somewhere in it, small and warm and sealed, an ocean waiting in the dark. Margaret Kivelson published her Europa paper in 1998. She was 60 years old. She had spent the prior 2 years building the case carefully, cross-checking flyby data, running the alternative explanations to ground, making certain the signal was what it appeared to be before she put her name on it in a journal that the entire field would read. When the paper came out, some colleagues were immediately convinced. Others took longer. A few spent years looking for the flaw in the analysis and didn't find one. She spent the following 2 decades advocating for a dedicated Europa mission, not loudly, not in the way that advocacy sometimes becomes performance, quietly, persistently, in the way scientists advocate for things they believe in, by continuing to do the work, by training students, by staying in the conversation long after it would have been reasonable to hand it to someone younger and step back. She was 86 years old when Europa Clipper lifted off from Kennedy Space Center on the 14th of October, 2024. She watched it leave the ground. The graduate students who worked on the early Galileo flyby data in the late 1990s are department chairs now. Some of them lead instrument teams on the Clipper. The postdocs who ran the first Hubble plume analysis have their own postdocs, their own labs, their own students who were children when the Hubble detections were published and are now early career researchers contributing to mission planning for a spacecraft those children never imagined they would one day work on. The work passes between people the way all long work does, not in a single handoff, not in a ceremony, but gradually, the way knowledge always moves, through conversations and papers and the slow osmosis of one person's understanding becoming another person's starting point. Nobody coordinates it. Nobody plans the generational relay. It happens because the question keeps being interesting enough that each new generation of people capable of working on it chooses to. That choice, repeated independently by hundreds of people across 4 decades, is its own kind of answer to something. Not to the question of what lives in Europa's ocean, to the question of what kind of creature asked the question at all. Somewhere tonight, a child is looking at Jupiter. Bright and steady in the south, the way it always is when it's up.
not twinkling the way stars do, but holding its light in a fixed, calm point that the eye returns to without being told to. The child doesn't know yet what they're looking at beyond the name, doesn't know about the magnetic field anomaly or the carbon dioxide or the ice-penetrating radar making its way toward the outer solar system on a spacecraft that left Earth 6 months ago. They just know it's bright and steady and somehow worth looking at twice. There is a reasonable chance, not a certainty, not a guarantee, but a real and reasonable chance that the person who first confirms what lives in Europa's ocean, or first confirms that nothing does, is alive right now, somewhere, looking up, or not yet old enough to look up, or looking at something else entirely and not yet knowing that one night they will point their attention at that small cracked moon and spend the rest of their career trying to understand it. The thread is still being pulled. It won't stop tonight. The ice is still there. The frost settled in the low places, soft and undisturbed. Jupiter filling the sky, banded and amber and slow. The long cracks running in every direction across the frozen plains, rust-colored and ancient, carrying in their chemistry the quiet signature of something below. And below the frost and the cracked plates and the long amber light, something moves. Liquid, dark, vast. It has never once seen light. It does not know a spacecraft is coming. It does not know 4 centuries of human curiosity have been aimed, however indirectly, at the frozen surface above it. It does not know that the question of what it is, or whether anything within it is, in any sense, alive, is one of the oldest questions a conscious mind has ever formed, and one of the last the instruments of science have not yet reached. It simply holds itself in the dark, patient, complete, unchanged. Some questions are worth a lifetime of looking. This is one of them. If this night spent alongside Europa, the ice, the ocean, the long human thread of curiosity aimed at a small cracked moon, brought you something quiet, we're glad you were here. There are more like this waiting. Oceans and moons and deep time, all at the same pace, all through the night. Find the playlist and let it run. Until next time, rest well. The ocean below the ice will still be there tomorrow. The surface of Europa is still. It has always been still, in the way that very cold and very distant places are still. Not the stillness of something waiting to move, but the stillness of something that has arrived at exactly what it is and has no reason to be otherwise. The ice stretches outward in every direction, pale and wide, and softly lit by the amber glow of Jupiter, hanging enormous and unhurried in the dark above, its banded clouds moving in their slow and ancient arcs, turning without urgency, without destination, without any awareness of the small frozen moon below them, reflecting their light back into space. The frost settles in the low places. It settles the way it always has, in the shadows along the ridge lines and the deep edges of the fracture zones, fine and soft and cool, undisturbed by any wind because there is no wind here, undisturbed by any season because there are no seasons here, only the slow rhythmic pull of Jupiter's gravity flexing the world from within, and the long unbroken continuity of a cold that has no memory of warmth and no expectation of it. The ice holds everything gently, the way deep places hold things, without effort, without intention, simply by being what they are, and having been that way for long enough that holding has become the natural condition, the default, the only state the place has ever known. The plates of the surface press against each other at their edges,
where they have slowly met across the long ages, raising low ridges that catch Jupiter's light on one face and fall into shadow on the other. And the shadow is very dark here, and the light is very soft, and neither one disturbs the silence that sits over all of it, like something settled and complete. The ocean holds its silence, deep below the ice. It holds it in the way the ocean has always held it, without choosing to, without knowing that it does, simply persisting in the dark beneath the frozen ceiling the way water persists anywhere it has found a space and a temperature that allows it to remain itself. Liquid, slow, patient, in no hurry to be asked anything, or to answer anything, or to be anything other than exactly what it is in this particular moment of a history so long that the word history stops meaning what it usually means. The cold descends from the surface, downward through the ice, in a slow gradient, cooling the upper layers where the ice is oldest and most rigid, softening slightly as it deepens toward the place where the pressure and the rising warmth from below hold the water at the narrow boundary between solid and liquid. A boundary that has existed for 4.5 billion years, without resolving in either direction, balanced and still and perfectly itself. Below the ice, the darkness is total. It is the kind of darkness that has no edges, no texture, no reference points against which the eye could orient itself, even if an eye were present to try. The water absorbs everything and reflects nothing. It simply holds the dark the way it holds everything else, completely, without remainder, without any space where the dark ends and something else begins. The pressure is everywhere and even, the way deep water holds pressure, surrounding rather than pressing. A total and gentle weight that is simply the condition of existing here, rather than anything imposed from outside. The warmth rises from the floor in slow columns. It rises the way warmth always rises, following the physics of lighter things moving through heavier ones, carrying with it the dissolved minerals and the quiet chemistry of a rocky seafloor that has been doing what rocky seafloors do for longer than any surface has existed on Earth. The columns move upward through the dark water without urgency, without haste, spreading as they rise and cooling as they spread, and eventually becoming indistinguishable from the water around them, their warmth absorbed, their minerals distributed, their slow upward journey completed, without ceremony and without witness. The ocean holds its silence, deep below the ice. The surface above is still. Jupiter turns. The frost settles. The aurora threads along the southern horizon in its soft and patient pulse, blue and faint and ancient, a shimmer that has been there since before the first atmosphere formed on the first rocky world in this solar system, and will be there long after the last one thins and disperses into space. There is no urgency here. There has never been urgency here. The concepts that carry urgency, deadlines, schedules, the pressure of time running in one direction with something important at the end of it. These are the inventions of minds that live briefly and know they do. Minds that developed urgency because they needed it, because their time was short, and the things they wanted to do were many, and the gap between the two required constant management. This place knows nothing of that gap. This place has time the way the universe has space, not as a resource to be managed, but as the medium everything else happens inside. The given condition that requires no justification and no conservation, because it is simply there, all of it, as much as anything could ever need. The ice is old. It is older than the oldest rock on Earth's surface, older than the oldest ocean sediment, older than the first cell that divided in the first warm pool on the early Earth and began the long and improbable chain of chemistry, becoming biology, that eventually produced the kind of mind that looks up at a sky full of points of light and wonders what they are. The ice was here before the wondering. It will be here after, in all likelihood, unchanged in the ways that matter, cold and still, and lit by the slow amber light of Jupiter, holding within it the dark ocean that has always been its secret and its center. The ocean holds its silence, deep below the ice. And the silence is soft. It is not the silence of emptiness. It is the silence of fullness, a space so completely occupied by its own nature that there is no room for anything else. No gap where sound could begin. No disturbance that the stillness hasn't already absorbed and made part of itself. The silence of water in the dark. The silence of cold that has no reason to change. The silence of a world that has arrived at its own equilibrium and held it, without effort, across a span of time that the word ancient is not quite large enough to contain. The frost settles. Jupiter turns, slow and amber and enormous, its bands drifting in their long arcs across the face of the gas giant that has held this moon in its gravity since the solar system was new, that will hold it long after tonight is over, and the night after that, and all the nights between now and whenever the sun expands and the distances change. And even these long, slow rhythms are finally interrupted. For now, the orbit continues. The tidal forces flex the interior. The ice holds. The ocean waits. And somewhere on the surface, in the shadow of a raised ridge, where the frost lies deepest and softest, where Jupiter's light falls at the shallowest angle and the cold is most complete, the stillness is so total and so deep that it feels less like a condition and more like a presence. The presence of a place that has been exactly itself for longer than the concept of exactness has existed anywhere nearby, and is in no hurry to become anything else. The ocean holds its silence deep below the ice. It always has. The frost settles in the low places, soft and fine and still. Jupiter fills the sky, amber and slow. The ice stretches outward in every direction, cracked and ancient and pale, carrying in its rust-colored lines the quiet signatures of the dark water below. Patient as everything here is patient. Silent as everything here is silent. Waiting in the only way that a place without awareness can wait, by simply continuing to be, unchanged and unhurried, in the long, slow dark. The stars drift overhead, cold and distant and steady. The silence holds. The ice holds. The ocean holds. And the night continues, soft and deep and still, the way nights always continue in places where time moves at the pace of the things that have no reason to hurry, where the cold is the oldest thing and the dark is older still, and somewhere far below all of it, in the warmth that rises slowly from the floor of a world that has never been asked a question, everything rests.